Automotive active suspension system. An active suspension is a type of automotive suspension on a vehicle. It uses an onboard system to control the vertical movement of the vehicle's wheels relative to the chassis or vehicle body rather than the passive suspension provided by large springs where the movement is determined entirely by the road surface. Active suspensions are divided into two classes, real active suspensions, and adaptive or semi-active suspensions. While semi-adaptive suspensions only vary shock absorber firmness to match changing road or dynamic conditions, active suspensions use some type of actuator to raise and lower the chassis independently at each wheel. These technologies allow car manufacturers to achieve a greater degree of ride quality and car handling by keeping the tires perpendicular to the road in corners, allowing better traction and control. An onboard computer detects body movement from sensors throughout the vehicle and, using that data, controls the action of the active and semi-active suspensions. The system virtually eliminates body roll and pitch variation in many driving situations including cornering, accelerating, and braking. Skyhook theory is that the ideal suspension would let the vehicle maintain a stable posture as if suspended by an imaginary hook in the sky, unaffected by road conditions. Since an actual skyhook is obviously impractical, real active suspension systems are based on actuator operations. The imaginary line, of zero vertical acceleration, is calculated based on the value provided by an acceleration sensor installed on the body of the vehicle, see Figure 3. The dynamic elements comprise only the linear spring and the linear damper, therefore, no complicated calculations are necessary. A vehicle contacts the ground through the spring and damper in a normal spring-damper suspension, as in Figure 1. To achieve the same level of stability as the skyhook theory, the vehicle must contact the ground through the spring, and the imaginary line with the damper, as in Figure 2. Theoretically, in a case where the damping coefficient reaches an infinite value, the vehicle will be in a state where it is completely fixed to the imaginary line, thus the vehicle will not shake. Active suspensions, the first to be introduced, use separate actuators which can exert an independent force on the suspension to improve the riding characteristics. The drawbacks of this design are high cost, added complication and mass of the apparatus, and the need for frequent maintenance on some implementations. Maintenance can require specialized tools, and some problems can be difficult to diagnose. Hydraulic actuation. Hydraulically actuated suspensions are controlled with the use of hydraulics. The first example appeared in 1954, with the hydropneumatic suspension developed by Paul Mages at Citroën. The hydraulic pressure is supplied by a high-pressure radial piston hydraulic pump. Sensors continually monitor body movement and vehicle ride level, constantly supplying the hydraulic height correctors with new data. In a matter of a few milliseconds, the suspension generates counter forces to raise or lower the body. During driving maneuvers, the encased nitrogen compresses instantly, offering 6 times the compressibility of the steel springs used by vehicles up to this time. In practice, the system has always incorporated the desirable self-leveling suspension and height-adjustable suspension features, with the latter now tied to vehicle speed for improved aerodynamic performance, as the vehicle lowers itself at high speed. This system performed remarkably well in straight-ahead driving, including over uneven surfaces, but had little control over roll stiffness. Millions of production vehicles have been built with variations on this system. Electronic actuation of hydraulic suspension. Colin Chapman developed the original concept of computer management of hydraulic suspension in the 1980s to improve cornering in racing cars. Lotus fitted and developed a prototype system to a 1985 Excel with electro-hydraulic active suspension, but never offered it for sale to the public, although many demonstration cars were built for other manufacturers. Sensors continually monitor body movement and vehicle ride level, constantly supplying the computer with new data. As the computer receives and processes data, it operates the hydraulic servos, mounted beside each wheel. Almost instantly, the servo-regulated suspension generates counterforces to body lean, dive, and squat during driving maneuvers. Williams Grand Prix Engineering prepared an active suspension, devised by designer aerodynamicist Frank Durney, for the team's Formula One cars in 1992, creating such successful cars that the Fédération Internationale de l'Automobile decided to ban the technology to decrease the gap between Williams' F1 team and its competitors. Computer Active Technology Suspension, CATS, coordinates the best possible balance between ride quality and handling by analyzing road conditions and making up to 3,000 adjustments every second to the suspension settings via electronically controlled dampers. The 1999 Mercedes-Benz CL Class, C215, introduced active body control, where high-pressure hydraulic servos are controlled by electronic computing, and this feature is still available. Vehicles can be designed to actively lean into curves to improve occupant comfort. Active Anti-Roll Bar. Active anti-roll bar stiffens under command of the driver or suspension electronic control unit, ECU, during hard cornering. First production car was Mitsubishi Mirage Cyborg in 1988. Electromagnetic recuperative. Main article, Electromagnetic suspension. In fully active electronically controlled production cars, the application of electric servos and motors married to electronic computing allows for flat cornering and instant reactions to road conditions. The Bose Corporation has a proof-of-concept model. The founder of Bose, Amar Bose, had been working on exotic suspensions for many years while he was an MIT professor. Electromagnetic active suspension uses linear electromagnetic motors attached to each wheel. It provides extremely fast response and allows regeneration of power consumed by using the motors as generators. This nearly surmounts the issues of slow response times and high power consumption of hydraulic systems. Electronically Controlled Active Suspension System (ECAS) technology was patented by the University of Texas Center for Electromechanics in the 1990s and has been developed by L3 Electronic Systems for use on military vehicles. The ECASS-equipped Humvee exceeded the performance specifications for all performance evaluations in terms of absorbed power to the vehicle operator, stability, and handling. Active Wheel. Michelin's Active Wheel from 2004 incorporates an in-wheel electrical suspension motor that controls torque distribution, traction, turning maneuvers, pitch, roll, and suspension damping for that wheel, in addition to an in-wheel electric traction motor. Audi Active Electromechanical Suspension System introduced in 2017. It drives each wheel individually and adapts to the prevailing road conditions. Each wheel has an electric motor which is powered by the 48-volt main electrical system. Additional components include gears, a rotary tube together with internal titanium torsion bar and a lever which exerts up to 1,100 Nm, 811.3 lb-ft, on the suspension via a coupling rod. Thanks to the front camera, the sedan detects bumps in the road early on and predictively adjusts the active suspension. Even before the car reaches a bump in the road, the preview function developed by Audi transmits the right amount of travel to the actuators and actively controls the suspension. The computer-controlled motors can sense imperfection on the road, and can raise the suspension up from the wheel which would go over the undulation, thus aiding the ride quality. The system will direct the motors on the outside to push up or pull down the suspension while cornering. This will result in a flatter drive and reduced body roll around corners, which in turn means more confident handling dynamics. Adaptive and semi-active. Adaptive or semi-active systems can only change the viscous damping coefficient of the shock absorber, and do not add energy to the suspension system. While adaptive suspensions have generally a slow time response and a limited number of damping coefficient values, semi-active suspensions have time response close to a few milliseconds and can provide a wide range of damping values. Therefore, adaptive suspensions usually only propose different riding modes, comfort, normal, sport, corresponding to different damping coefficients, while semi-active suspensions modify the damping in real time, depending on the road conditions and the dynamics of the car. Though limited in their intervention, for example, the control force can never have different direction than the current vector of velocity of the suspension, semi-active suspensions are less expensive to design and consume far less energy. In recent times, research in semi-active suspensions has continued to advance with respect to their capabilities, narrowing the gap between semi-active and fully active suspension systems. Solenoid/valve actuated. This type is the most economic and basic type of semi-active suspensions. They consist of a solenoid valve which alters the flow of the hydraulic medium inside the shock absorber, therefore changing the damping characteristics of the suspension setup. The solenoids are wired to the controlling computer, which sends them commands depending on the control algorithm, usually the so-called skyhook technique. This type of system is used in Cadillac's Computer Command Ride (CCR) suspension system. The first production car was the Toyota Sora with semi-active Toyota electronic modulated suspension, from 1983. Magnetorheological damper. Main article, Magnetorheological damper. Another fairly recent method incorporates magnetorheological dampers with a brand name Magneride. It was initially developed by Delphi Corporation for GM and was standard, as many other new technologies, for Cadillac STS, from model 2002, and on some other GM models from 2003. This was an upgrade for semi-active systems, automatic road sensing suspensions, used in upscale GM vehicles for decades. It allows, together with faster modern computers, changing the stiffness of all-wheel suspensions independently. These dampers are finding increased usage in the US and already leases to some foreign brands, mostly in more expensive vehicles. This system was in development for 25 years. The damper fluid contains metallic particles. Through the onboard computer, the damper's compliance characteristics are controlled by an electromagnet. Essentially, increasing the current flow into the damper magnetic circuit increases the circuit magnetic flux. This in turn causes the metal particles to change their alignment, which increases fluid viscosity, thereby raising the compression/rebound rates, while a decrease softens the effect of the dampers by aligning the particles in the opposite direction. If we imagine the metal particles as dinner plates, then whilst aligned so they are on edge, viscosity is minimized. At the other end of the spectrum they will be aligned at 90 degrees south flat, thus making the fluid much more viscous. It is the electric field produced by the electromagnet that changes the alignment of the metal particles. Information from wheel sensors, about suspension extension, steering, acceleration sensors, and other data, is used to calculate the optimal stiffness at that point in time. The fast reaction of the system, milliseconds, allows, for instance, making a softer passing by a single wheel over a bump in the road at a particular instant in time.